This is video 3 for the rotation unit. For this one, we're going to start talking about torque. But before we do that, we have to understand moment of inertia. You will remember that inertia is the tendency of an object to maintain a state of motion. So, if an object's at rest, it's going to try to stay at rest. If it's moving, it's going to try to keep moving at a constant velocity, which means same speed and same direction. How about rotating objects, though? If we have a large disk, like a merry-go-round on a playground, it's kind of hard to stop it from rotating. It's also hard to get it to rotate to begin with. So this tendency to maintain a state of rotational motion is what we call moment of inertia. We use a capital I to as its variable, and what it comes down to is it depends on the placement of mass. So let's say we have a solid disk and a ring. Each of them have the same mass and the same radius. Since all of the mass for the ring is located at its edge, it's going to be harder to give it an angular acceleration than the disk. So that's one reason when you look at competitive bicycling, you'll see that some of the wheels, or some of the cyclists, use solid wheels instead of spoked rims. It's easier to get a disc to accelerate and to get it to stop. Since it depends on the placement of mass, we have several formulas for moment of inertia for different objects. So for a plain ring or a cylindrical shell, it's going to be I equals mass times radius squared. If we have like a ring with like a thick wall, we can it's a little more complicated. We compare the two radii, and it's just like the first radius squared plus the second radius squared. So like radius r1 would just be to like the inside, and then radius r2 would be to the outside. And notice for a disk, the moment of inertia is 1/2 mr squared. So just looking at between the disk and the ring, we see that the disk has half the moment of inertia as a ring does. And we have all kinds of other geometry that we can take a look at. Let's say we have something kind of weird. If I wish to find the moment of inertia of something different, I can take a look at this formula right here. So this would be the moment of inertia at the, now cm means center of mass. So the moment of inertia at the center of mass plus md squared, where d is the distance between the center of mass and where you're trying to rotate the object. We also have the moment of inertia equaling the sum of all individual moments of inertia. We're not going to deal with that too much. I'll show you some problems in class to give you a better idea of that. All right, so let's take a look at something. What's the moment of inertia of a door? Well, we can think of a door as a lot of thin rods stacked up. So if I were to draw a picture of a door, where this line represents the axis, where it's going to rotate around, I can visualize this door as a bunch of thin rods stacked on top of each other. The moment of inertia for a thin rod that's being rotated about its end is 1/12, I'm sorry, 1/3 mass times length squared. So the truth is, this is the same as the door. It's just that we have a bunch of masses added together. So it's the total mass of the door and the length of the door. Let's find something else. Let's find the moment of inertia for this object. So it's a thin rod, but we're trying to rotate it at a point 1/8 of the distance in. So to do this, we're going to use that formula where moment of inertia equals the moment of inertia at the center mass plus md squared. Now this formula does have a name. It's called the parallel axis theorem. So we're going to use the parallel axis theorem to help us solve this. So first off, I'm going to draw a line representing the center of mass. D is going to be this distance where we're trying to rotate it, the distance between where we're trying to rotate it and the center of mass. The rest of this length, as you might imagine, is going to be L over 2. You know, the center of mass for this rod is right at the center. Okay, so the moment of inertia at the center of mass for a thin rod is 1/12 ml squared. And you can find that from the geometry, or you can find it from the formulas I provided just above this. Plus, now for D. Looking at D, I see that it's going to be L over 2 minus L over 8. That's what D is. Now I just have to do a little bit of math. So find the common denominator, add them together. Three squared is 9, 8 squared is 64, L squared is L squared. And then at this point you can just plug it into your calculator. And there you have it. Now, the units for moment of inertia are always kilogram meters squared. On the AP exam, you will not be asked to use the parallel axis theorem. In fact, they probably won't even bother having you use the geometry. They're just going to give you it. So whenever you see some number followed by kilogram meter squared, that is I. That is your moment of inertia. So this is just one step, or one instance where I'm kind of going a little above and beyond. So torque. The presence of a net torque along any axis will cause a rigid system to change its rotational motion, or an object to change its rotational motion about that axis. Really, you can think of torque as a force, but a rotational force. A linear force is meant to change an object's position or to cause it to move. A torque is something that's trying to get something to rotate around an axis. So torque is kind of like force. Now, rotational motion can be described in terms of angular displacement, angular velocity, angular acceleration. We've talked about that. Rotational motion of a point can be related to its linear motion using the distance. So basically, you know, that whole V equals R times omega. That's just saying we've got the bridge stuff. Angular acceleration of an object or rigid system can be calculated from the net torque and the rotational inertia. So that's where we're getting into next. Torque is the rotational force needed to spin something. So remember that Newton's second law told us that the net force equals mass times acceleration. Well, now we can say the net torque equals moment of inertia times angular acceleration. So I is like the rotational equivalent of mass, and alpha is the rotational equivalent of acceleration. So torque, tau, we use the Greek letter tau for torque, is the rotational equivalent of force. I'll talk about this a little bit later, but we can also find torque as a force times a perpendicular force times a lever arm distance, and we'll talk about this a little later, but that's important to know also. So what this means is that the math we use is identical to the math for linear accelerations. So for example, what torque is needed to accelerate a bicycle rim if I'm modeling it as a spoked rim? Well, the net torque equals I times alpha. So for a spoked rim, the moment of inertia of a rim is mass times radius squared. So this net torque needed would be mr squared times alpha. Okay, let's revisit the modified Atwood's machine. Now, in the past, we used an ideal pulley, which meant that it had no mass and no friction. Now we're going to use a real pulley. So it does have mass. We're still going to ignore friction because it's still small. Okay, looking at this, also we're going to assume that this is frictionless, a frictionless surface. So we don't have to worry about that. This is going to be mass 1. This is going to be mass 2. And we're just going to say the pulley has mass. There's going to be some tension. There's going to be some weight. And this system is going to rotate, or this pulley is going to rotate clockwise. Now, because this pulley has mass, that means the tension on both sides of the pulley will be different. That's why we have a T1 and a T2 this time. So the way we're going to analyze this is really the same way that we did the regular Atwood's machine. We're going to look at a force diagram for each individual object. So let's start with M1. So for M1, we just have one force acting on it. That's T1. It has a positive acceleration. So the net force acting on object 1 equals T1, which equals mass 1 times acceleration. So T1 equals M1A. That's going to be my first equation. Then I have the pulley. So for the pulley, this time instead of a net force, we have a net torque. That's going to equal I times alpha. And since it is going clockwise, it's negative, because clockwise rotation is negative. Now, torque is a perpendicular force times a lever arm distance. So we have T1 as our force, and then the lever arm distance is going to be the radius of this pulley, minus T2. So notice how T1 is trying to rotate this counterclockwise. So T1 is trying to do positive torque. T2 is trying to rotate this clockwise. So it's trying to do negative torque. Obviously T2 wins, but that's where I'm getting the positive and negative for the tension 1 and the tension 2. The moment of inertia for this solid disk is 1/2 mass times radius squared. And then our bridge formula says that acceleration equals r times alpha, so alpha equals acceleration divided by the radius of our pulley. Now I'm doing this because I want to get rid of alpha. I want this all in terms of a, linear acceleration. Okay, now I can do some math here. I can factor out an r, so I got t1 minus t2 times r equals negative 1/2 m. Now notice that we have some canceling here. The r is an r squared, so I got this r times acceleration. Notice once again, r's are going to cancel. And I'm going to call this right here equation 2. Now I'm going to take a look at mass m2. That's my third object. And looking at this, I have sum of forces acting on object 2 equals that T2 minus how much this thing weighs, and equals M2A. And it's negative because M2, when I take a look at this, it's going to have a negative acceleration. I'm going to call that equation 3. Now, I solved that for T2 because what I'm going to do is I'm going to take this equation, I'm going to plug that in for T1. I'm going to take this, I'm going to plug that in for T2. So what I'm left with then is I've got this M1A minus this M2G minus M2A equals 1/2 MA. Ooh, negative. At this point, I just got to get my A's on the same side. Ooh, and I think I made one tiny mistake. Let me back up just 1 second here. This was minus T2. So I should have this in parentheses. What that does is makes it M1A minus M2G plus M2A. There we go. And then I find that the acceleration gives me that expression right there. It should look very, very similar to the expression we got for just two masses hanging on a pulley, except now we have to include the mass of the pulley. So notice that before that there was this force acting on the pulley, and the force is perpendicular to the radius of the pulley. So this is where we're going back to how torque, we can find torque with the force times the lever arm distance. This also introduces us to a new way of multiplying vectors, the cross product. So to get the magnitude of this torque, we would have the force times this lever arm distance times sine of the angle between them, because we have to make sure that the force is perpendicular to the lever arm. Looking at this picture right here, if I want to rotate this arm, I would need to have this force right here. Only forces perpendicular to the arm will rotate it. Ones parallel will not. So notice how I can use the sine function to figure out what that perpendicular force is. Now to get the direction, we use the right-hand rule. So for the right-hand rule, the force...
Math department meeting scheduled for this morning is canceled. Math department meeting scheduled for this morning is canceled. Thank you.
Using your right hand, your fingers, your four fingers, point in the direction of the force. The R points in the direction of your thumb. And then your palm will point in the direction of the torque. So, looking at this example right here, our fingers would be pointing up. Our thumb would be pointing this way, so the torque would be coming out of the board at us. And I'll explain that in a little more detail in class. So again, notice that only force components that are perpendicular to the line connecting the axis of rotation and the point of application of the force result in a torque. So we have to make sure that we do use the cross product, or at least make sure that that force is always perpendicular to your lever arm distance.